let's say that you're standing with a rope in your hand and you give it a little flip. Then what that does is it creates a pulse on the rope that travels down the rope. So that's a traveling wave that you've created. So here you are standing and you have a rope in your hand, and if you give it a little flip, let's say the rope is tied to the wall over here, and you've given it a little flip. So what could happen is that the rope might create a little pulse like that, you know, because you've moved your hand up and down. And so that pulse then travels forward till it gets to the end of the wall, right? That's a really good analogy for particles having a wave character. Because if you imagine that there's a particle here instead of this pulse that you've created, then there's a width to the wave as it passes, as it moves through space. And for large particles, that width is so narrow that it has no consequence as to its motion. But for very tiny particles, the width actually can be larger than what we would define the size of the particle to be. So we would say, well, is that particle right in the middle of that wave, or is it over here, or is it over here? We can kind of think of the wave as a probability of the particle being in a particular place. So the wave does have a maximum right there, and we could say that that is the most probable position of the particle, but there's also a little bit of a uncertainty. And there's actually something called the uncertainty principle, Heisenberg's uncertainty principle, which states this mathematically for particles, what the size of that uncertainty is. But for electrons orbiting around the atom, that uncertainty is close to the size of the atom itself. So if an electron is orbiting an atom, but we're not really sure where it's at as it goes around there, and that uncertainty covers the entire atom, then what effect does that have on our description of the orbit of the electron? Well, that's the quantum mechanical atom. Now, the description of the nucleus doesn't change because it's not moving, it's just staying there with respect to the electrons. But now, where before we had this Bohr orbit, and actually several of them as we go out. Remember, those were quantized. Those came in predefined distances from the nucleus. And we talked about that we could number those. So we use the letter n to number those. That would be n equals 1, n equals 2, n equals 3. So this picture right here, this is the Bohr model. Well, let's picture as the electron's moving around, if it's got this uncertainty to it, if it's got this wavelength, and let's imagine the wave is like this around that electron. There's that uncertainty that I mentioned. Well, then there's really a distribution as to where the particle could be. It's a probability distribution. Sometimes we could picture that as a cloud. To me, in my mind, that's the easiest way to imagine the electron, is spread out like a cloud. The electron's really not really exactly on that orbit, but it's distributed around it, and its most probable position would be the same radius as the Bohr model gives us, but it's a fuzzy picture now. Okay, so that particular shape that we get from that distribution, that's called an s orbital. So, and because it's at n equals 1, we combine the number and the letter, and we say that that's a 1s orbital. Right there. You have the same thing out here. For the electron was out here, it would also have its distribution spread out. And since that's at n equals 2, that spherical shape would be a 2s orbital. And then we'd have a 3s orbital out here. They just keep getting bigger as we go further out and have higher numbers of n, so this would be a 3s. Okay, now, it would be nice if it was just that simple, or that, close to the quantum mechanical picture, but it's not quite. There's a little bit more complication to it. The Bohr model has a restriction as to how many electrons can be in an orbit, in any one particular orbit, and it depends on quantum number n. For the smallest orbit, you can have 2 electrons. For the next higher orbit, you can have 8 electrons altogether, and then it goes up from there. It would be the number of electrons you could have would end up being n squared, 2n squared. So that's where you get 8 here. And then this one would be, that'd be 18 here, because 3 squared is 9 times 2 is 18. So it'd be 2, 8, 18, and then on up. Well, in quantum mechanics, it turns out you can only have 2 electrons in every fuzzy picture like this, in every orbital. So that means that for here, that's fine, because you can only have 2. You only need 2 electrons in that lowest level. But once you get out here, if you say you can only have 2 electrons in this spherical shape, then you still have 6 more electrons to fit in there. And they would have to then end up being in different types of orbitals. You'd have to have more than just that 2s orbital that exists there. And you do. The other orbitals that exist there are called p orbitals, and they have a different shape. I'm going to draw the shape of the p orbital kind of to the side here. So I'm actually going to summarize these shapes. So you have an s orbital, that's the spherical shape, and then that can come in different sizes. Then you have a p orbital, so these are orbitals. Notice also that I'm using the word orbital now, not orbit. And those are different things. When you go to the probability picture, quantum mechanical picture, you call them orbitals. In the Bohr model, they were orbits. They were classical orbits. The P one has this kind of shape. It's usually referred to as a dumbbell. Okay, that would be a dumbbell shape. And that also can be at different sizes. But that shape doesn't exist here. It just exists starting in this level. So let me try to draw that. The picture gets complicated when you start putting those other shapes in. But let me just at least draw one of those p orbitals here. So that would go like this. Okay, so kind of on top of the s orbital. It's the same size as the 2s. It's roughly the same scope, but it's a completely different shape. Okay, so the electron there would have a probability of being in that, anywhere within that, whereas again, though, the most probable radius would be out here, even for the p orbital. But that would be labeled as a 2p, that one that has that dumbbell shape. But that's still 2 electrons in the s here and 2 electrons in the p. That's only 4. We still need 4 more to get our 8 electrons in this level. So there's actually 2 more like this in that same shape, but they're in different directions. So another one would go like this. It's still a p orbital, but it would be going up and down. So I could add that one to the picture also. And of course, it keeps getting more complicated as I add these pictures, but it would be going up and down, perpendicular to the other one. And then there's actually a third one that comes out of the Bohr as well. So there's 3 p orbitals, each holding 2 electrons at most. And then the 2s holds the other two, and that adds up to 8. Then there's also another shape that has its letter designation as a d orbital, and that's sort of a four-leaf clover type shape. And you won't have to remember the shape, but just so you know that there's this other shape that also is in here, but it's not at this level. That third shape comes in starting with the next level. Each level you go up introduces a new shape, or what's called a new sublevel. And that's how quantum mechanics describes the atom. For the D's, though, there's 5 of those, because the next level has to have 18. So if you have the 2 here and the 6 from these 3, and then if you have 5 more orbitals, that's 10 more, and that adds up to 18. So I'm not going to draw those in, because obviously that would get way too complicated in the picture. But just so you know, you keep adding more levels as you go up in the orbitals. There's another one that's important also. It has the letter F. I'm not going to draw its shape at all, but there is an F orbital as well that you can have in this picture. And it's kind of similar to the D, except it has more lobes. It has even more than 4. So that's kind of the picture of the quantum mechanical atom, which is very complicated looking. So what we're going to do is kind of simplify it by going back to that energy level picture that we use to describe transitions. And in the energy level picture, you don't have to worry about fitting it all into the same place. All we're going to do then is look at the energies of these, and then we can kind of see how the quantum mechanical model of the atom is mapped out